Today's Wednesday, the 31st of March. Last Monday, we looked at Chapter 7 using Cengage homework. But we used the homework problems from Cengage that were not selected for grading purposes. Now today, I want to look at the review document that is provided in Blackboard. It has the same form as a hard copy exam. So the questions are going to be, let's see, I think they're all multiple choice. Let me check to be sure. Yeah, it looks like it. So for this class, the way the exams are administered, the exam that you download will look exactly like this one. It gives you a sense of familiarity. But let me share that document, and I'll share the key to the review document, if it'll cooperate here. There we go. And I think that's big enough for everybody to see it. So there we have Exam 5, Chapter 7, and it's still on the topic of atomic structure and periodicity. Once we finish this chapter, the last two chapters we get into try to explain the nature of the chemical bond itself. Just giving you a little teaser for from now till the end of the semester. And we will have a final exam, which will be comprehensive. Okay, so I've got some picked out here that I want to look at, and I'll check them off as we go. Okay, let's look at number 1. I don't have 1 checked, but I think we'll do 1 and 2. Okay, let me try one of these older ones and see if I can get some more life out of them. So number 1, says when uranium is ignited, when ignited, a uranium compound burns with a green flame. So the uranium compound, whatever it happens to be, produces a green color. So first of all, what does that mean? If the uranium compound, and we're assuming that the color is due to something that's happening to the uranium atom, not to what it's bound to. It's bound to a non-metal, I'm sure, but we're focused on uranium. So when uranium is, this compound is burned, it burns with a green flame. So what does that mean? You can have 2 types of, your eyes can receive 2 types of light. One that is produced by emission. That is, some atom emits light. Okay? In order to do that, it has to be excited first. In other words, electrons have to be sent out here, and then they have to return. And when they do that, they give off light. The other type of light that your eye can receive is actually the absence of, or absorption. This is emission. And you can also detect light by way of absorption. So the extreme example of absorption would be light shining through some element, a cloud or some element, and the electrons are excited in that. They go from here and they go out to a higher orbital. When they do that, they absorb the light. All right. So what light does your eye receive? Whatever is left over, right? If the light shining through it has multiple wavelengths, then your eye will receive whatever is not absorbed. In the extreme, if light is shining through something that absorbs multiple wavelengths, it's possible that all of the light is absorbed and you see nothing. You don't get anything. That would be black. That's what we call black. Whereas the emission spectrum of the sun is more or less continuous. It's white light, although we know it's slightly yellow. And if you use a spectrometer and split up the light into its individual wavelengths, you'll find that some of the wavelengths of light that are emitted by the sun are absorbed. Now, the short version is the sun emits light, and then the atmosphere. The sun has an atmosphere, believe it or not, absorbs some of that light. That way, we can tell by the absorption of those wavelengths of light what elements there are in the atmosphere of the sun. Okay, so let's get back to the question. The wavelength of the light given off by this flame is greater than that of. All right. So this green light is associated with some wavelength. And we want to compare it to red light. Let's see, infrared, radio, and ultraviolet, and yellow. Okay, so we need to think of the green light in terms of its wavelength relative to these other wavelengths. So if we draw ourselves that continuum, where this is wavelength and this is increasing wavelength. So this is high wavelength, this is low wavelength. Okay, the longer wavelengths are there. I should say that. This should say long wavelength. And this should be short wavelength. Okay, let's say green is right here, right? That's our green wavelength. Now, what happens when you go to longer wavelengths? Does the color, what happens to the color? When you get longer wavelengths, it moves toward the red. So remember the acronym, we didn't talk about it in class, but the acronym for the rainbow spectrum. Right? Red, orange, yellow, green, blue, indigo, violet. Well, this is actually shorter wavelength, and this is long wavelength. So it'd be the other way around. So if you go from green, you're actually moving this direction. So this would be yellow, this would be orange, this would be red. And then you'd have out here infrared, radio, that direction. This way, you'd go toward, from green, you'd go to blue, and then you go to indigo. I never understood what's the difference between indigo and violet. My eyes can't tell the difference, but it's there. Indigo, violet, and then as you get shorter wavelength, you go from violet to ultraviolet, and then you go to let's see, what's next? Ultraviolet, then X-ray, and then you go to gamma ray. So the shorter wavelengths are this direction. Okay, now with that understanding, which one of these has, go back to the question, the wavelength of light given off by this flame is greater than. So the wavelength of green is greater than what? Well, it's greater than blue. Is blue a selection? No. It's greater than indigo? No. It's greater than violet? That's not a choice. It's greater than ultraviolet. Aha, that's a choice. Wavelength is greater than ultraviolet. There are no others in there. So that's it. So if you look at the spectrum as a continuum like this, then it's easier to deduce the answer. Okay. Now let's look at number 2. We're going to be in a similar vein here. Which form of electromagnetic radiation has the longest wavelengths? Well, I probably should have left the spectrum up here. But let's look at these. And think of them in terms of energy also. Longer wavelength means lower energy. So gamma rays are, of this group, gamma rays are the highest energy, shortest wavelength. So that can't be it. X-rays, the next one up, that's still not the longest wavelength. How about infrared, right? Infrared is on the other end of the spectrum, past red. What's past that? Well, microwaves. Microwaves are past infrared. I left microwaves out of that group over there. And then radio waves are actually the longest wavelength of this group. Okay. All right. So let me mark myself off. I've done that one and that one. Let's look at number 3. Which of the following frequencies correspond to light with the longest wavelength? Okay, for this one, you have to remember the relationship between frequency and wavelength. The speed of light is the constant, and it's equal to the wavelength times the frequency. Okay, remember when you have a product that's equal to a constant, they're inversely proportional. That is, as the wavelength goes up, frequency goes down. Or as the wavelength goes down, gets shorter, the frequency goes up. Okay, so with that in mind, we're looking for the frequency that corresponds to light with the longest wavelength. So the longest wavelength will produce the smallest frequency. Right? If you get this one very long, this one will be short. Well, actually, that's not correct. Bad choice of words. If this one's long, this one will be low. Low frequency means long wavelength. Okay, so look at the units of measure here also. Reciprocal seconds. Seconds to the -1. That's the same thing as hertz. Right? Cycles per second. They're all synonymous. Okay, so we're looking for the one with, if it's the longest wavelength, we're looking for the lowest frequency. Right? So the first place I'd look is the power of 10. And only if you have 2 powers of 10 that are the same, then you go to the coefficient for the tiebreaker. But if we look at the powers of 10, we may be able to answer it without even looking at the coefficient. So we're looking for the low value of frequency. There's 13, 10 to the 13. 10 to the 5th is shorter than that, isn't it? I mean, smaller than that. 20, 12, 9. Looks like we found B. 4.12 times 10 to the 5th reciprocal seconds, or hertz, is the frequency associated with the longest wavelength. Right? And we can calculate the wavelength, right? You just put the value of frequency here and the value of the speed of light here, and you can calculate the wavelength. So what will the units be? The units will be in meters. Why? Because the speed of light is in meters per second. This takes care of the seconds, left over meters. Okay, that was 3. Let's see, let's move out of this page and go to the second page. Here we go. Look at number 6. Let's see, I have to keep adjusting this thing. He likes to walk. Number 6. Okay. Let's just, excuse me, read the question. A line in the spectrum of atomic mercury. So what do they mean by atomic mercury? That's it. The neutral atom. No charge. Atomic mercury. And it's separate. So that tells me that it's a gas. That's the only way you can get mercury separated from one atom, separated from another one, so that you can look at the atom itself and not any other interaction. Let's see, got another one showing up. Okay, that's good. More the merrier. So a line in the spectrum of atomic mercury has a wavelength of 254 nanometers. Okay, that's given information. When mercury emits a photon of light at this wavelength, the frequency of the light is what? So the question is, when it emits a photon of light, with that wavelength, what's the frequency? Okay, so we go back to the formula. There you go. Now, this is going to be 2.7, excuse me, 2.9979, I believe, times 10 to the 8th meters per second. Is that right? I had to check myself. Working from memory here. Yeah. 9979 10 to the 8th meters per second is equal to the wavelength. So that's not meters, is it? What is that in meters? The way I like to do it is look at the unit of measure. This is the standard, meters. The prefix modifies that standard. Nano means 10 to the minus 9th. So I take 254 times nano meters. So I take the nano and I put it right here. Right? You can change it to scientific notation if you want, but your calculator will accept the value like that. You just punch in 254. On my calculator, it's E. On yours, it may be 10 to the X, whatever. And then put in the exponent. So we can just leave it like that. Meters. times frequency. Now solve for frequency. So we say this one divided by that one equals that one. 2.9979 exponent 8. I'm going to store this in memory so I can use it again. There we go. Recall. Nope, something went wrong. Hold on, let me try that again. 2.9979 exponent 8. Enter. Now store it in memory. Store 8. There we go. Okay, now I'm going to divide it by that number. So I can punch in 254 and then my exponent minus 9 and divide that into that number. And I get 1.18 times 10 to the 15th. What are the units of measure? Well, when we divide this one into this one, that leaves the seconds, reciprocal seconds. Or we could say hertz. Same thing. Now let's see, is that one of the answers? Yeah, there it is. C. Right there. If you ever look at your radio dial anymore, most of the time people don't because they're all digital. But if you look at your FM dial, it'll say when you're dialing in the number, it's not hertz, it's megahertz, which means million hertz, correct? So what's a million? A million is 10 to the 6th. So 10 to the 6th here would be 9, 10 to the 9th. It'd be 1.18 times 10 to the 9th megahertz. And then that didn't get us anything extra. How about gigahertz? That takes 3 more out of that. 10 to the 6th gigahertz. That doesn't help much either. What about, what's the next one up? Terahertz, 10 to the 3rd more. So that would be 1.18 times 10 to the 3rd terahertz. Okay, that's enough said about that one. That's number 6. Let's move to number 8. Okay, number 8. Green light can have a wavelength of 543 nanometers. That's an interesting statement. Green light can have that wavelength. Our eyes receive light and interpret the wavelength by a chemical reaction. Other wavelengths that are close to that could also make them register as green in our brains. But in this case, 543 nanometers is green light. So the wavelength is 543 nanometers. The energy of a photon of light is what? Okay, now we're looking at Planck's equation that equates energy with frequency. Right? It says that the energy in joules is equal to Planck's constant times frequency. Right? We don't have frequency. So you've got 2 choices. You can calculate that, turn that into frequency, and then plug it in the formula. Or you can take the formula that you're going to use here to convert that to frequency and blend it with that one. That's what I like to do. So C equals lambda times frequency. And if we want to put frequency in there, we need to solve this equation for frequency, which is C divided by lambda. So now we can say Planck's constant times C divided by lambda is equal to energy. Okay, so now that we have our formula, we can plug in the values that we know. So energy is going to be equal to, and let's see, your review document has the Planck's constant. That's what H is. I think it's 6.6 something or other times 10 to the minus 34. I have to look it up too. Planck's constant. Where did you go? Here it is. 6.626 times 10 to the minus 34. Joules seconds. So it's like a compound unit. And that is times 2.9979 times 10 to the 8th meters per second. And wavelength is 543 nanometers. Okay, there we go again. We need meters. Right? So meters would be, I'm just going to put it down here, 543 times 10 to the minus 9th meters, right? I just took that nano, like I did before, and put it right there in front of the meters. Okay, are our units going to give us joules in the end? Well, meters down here cancels meters up there, right? And this seconds is in the denominator of the numerator, which puts it in the denominator. So the denominator here cancels seconds there. And that leaves us with joules. So we're good. By units we are. We have to be sure that our numbers are right, of course. But this is the thinking part. It's done. Now all you have to do is crunch numbers. So let's see. I want to call it my speed of light. I got it in memory now. Let's see. Recall. Nope, it didn't like that. All right, I'll punch it in manually. 6.626 exponent minus 35. Then 2.9979 exponent 8 times that, and then divided by this number. There we go. 3.66. Yeah, three significant figures. 3.66 times 10 to the minus 19. Okay, that's an awfully small number, right? That's how many joules are contained in one photon of light with that wavelength. So in order to transfer a lot of energy with that light, you would need lots of photons. Okay, well, let's see. Did I do the calculation correctly? Yep, there it is right there. C. All right, that was 8 8. Oops, I flipped the page already. There we go, 8. Now we're going to flip the page over to 11. Here we go. How many of the following statements are correct? Okay, so we have to look at each one individually and decide how many are correct. All right, so that's 11. All right, for the first one. The importance of the equation E equals mc squared is that energy has mass. Yeah, that's true. Mass is equivalent in certain respects to energy. If that equation were not true, we would not have access to atomic energy. Right? We'd still be burning coal and oil and trees or chasing that pie in the sky renewable energy that the current government is so fond of. But we wouldn't have nuclear energy. E equals mc squared is the central idea in nuclear power. In other words, and they do this, if you weigh the uranium that goes into, or just weigh the pellets that go into a nuclear reactor, and then you run it for a while, extract energy from it, and then you take those pellets out at the end of your cycle, their life cycle, and weigh them, they will weigh less. There will be less mass there than there was to begin with. And where did that mass go? It was converted into energy. Now, technically speaking, a chemical reaction will also convert if it gives up energy, if it's exothermic. It will convert some of the mass of the reactants into energy. Not always. I should qualify that. Some of that energy might be contained in the bonds. In fact, most of it is. But for all intents and purposes, and with the accuracy that we can measure chemical reactions, it still holds that conservation of mass is preserved. And conservation of energy and transfer is also preserved. So in chemical reactions, we can pretty much ignore E equals mc squared. But I is true. How about double I? Electromagnetic radiation can be thought of as a stream of particles called photons. Yeah, that's true. We just calculated one of them. How about triple I? Electromagnetic radiation exhibits wave properties. Well, yeah, of course. Otherwise, we wouldn't be able to talk of it in terms of wavelengths. That's true. How about IV? Energy can only occur in discrete units called quanta. We have to qualify that. Energy that is traceable to light or an interaction of light and matter is quantized. That's the fancy word for it. That is true in those terms. So, as far as that statement goes, it's true. So that means all of them are true. That's why E is the answer. All four of those are true statements. All right, that was 11. Oh, now we're going to do 12, 13, 14, 15. And they're all based upon these four questions. They're all based upon this information given right here. So, Let's do them all together. We're going to start off with 12. And these statements, A, B, C, D, and E, include, well, let's see, what are we trying to do? From the following list of observations, choose the one that most clearly supports the conclusion in each of the subsequent statements. All right. What if we say electrons have wave properties? Electrons are like waves. Which one of those statements, A through E, justifies that conclusion? Emission spectrum of hydrogen? I don't think so. Photoelectric effect? Scattering alpha particles by metal foil? Diffraction. Diffraction is characteristic of waves. So what is diffraction? We'll just go back and look at the definition of diffraction. It's the ability of any form of matter or energy to sort of peek around a corner. Okay? Let's say we have a wall here, right? And you've got light coming in. Now, let's be consistent. You got electrons coming in from that side. If the electrons behaved as particles, right, they would smash up against that wall right there, right there. And once they reach the edge, they go straight on through. Like that. And there'd be a shadow over here. You would not be able to detect any electrons on this side of that wall if they were particles. But we can detect electrons over here, right? So that's not true. Electrons, in fact, behave as if this were a point source of energy. And they will form, I'll do like that. So now you can detect electrons out here, 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 all the way around. That's diffraction. Now, we most often use diffraction not with a wall, but with a slit or a pinhole. So you would have a slit here. It's very small. It's tiny. You have to look at it. You have to use a magnifying glass usually to see it, or a bright light behind it so that you can see the slit. And then anything impinging on that, whether it's an electron or a light wave, once it hits that point right there, it can be a wave on this side. But when it hits that point, it starts off as if that's the source of a new wave right there. Now, if you have two slits, then this one's going to produce waves also. And if you look at those dark lines as peaks, high points, and the troughs as low points, then you're going to get what's called an interference pattern. So over here on your detector, you can detect a bright spot there, and then there'll be a bright. Those bright spots are according to, bright spots are, I had the word on the tip of my tongue. Those bright spots correspond to constructive interference, where the peaks come together and they reinforce one another, or the troughs come together and they reinforce one another, which would be actually negative, would be dark spots. And that's characteristic of waves. You see that with electrons, you see it with light. Okay, so diffraction explains electrons, wave properties. How about 13? Electromagnetic radiation has wave characteristics. That's also diffraction. Out of those choices, the only one that is characteristic of wave property is D, diffraction. So 12 and 13 are both diffraction. How about 14? Same thing here, diffraction. How about 14? Electrons in atoms have quantized energies. Well, let's see. Think back to the PowerPoints in the lecture when we first encountered quantized energy. It was in terms of the line spectrum of hydrogen, right? It had 4 lines, each with its specific wavelength. The only reason that could happen is that the electron movement is quantized. In other words, electrons, that's the nucleus. Electrons only move between specific energy levels, or they could come back from this other direction, like that. That's the quantized nature of electron movement. They have those quantized energies, right? That explains, well, what explains that? The emission spectrum of hydrogen does explain that. The photoelectric effect, no. It doesn't explain the quantization of electron energy. The emission spectrum of hydrogen does very clearly speak to quantized energy levels that electrons move between. Okay, in 15, I'll have to scroll back to see spacing between atoms. Let's see, 15. Spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. All right. The key there is wavelength. If you're saying wavelength, the de Broglie wavelength of electrons, they're behaving like waves. So what can explain wave behavior out of all of these? The only one is still diffraction, right? None of the others explain waves. By the way, let's see. How about this scattering of alpha particles by metal foil? What does that explain? That explains the nuclear atom. That's it. It doesn't say anything about particles, or, well, it says something about particles, but it doesn't say in the terms that we're interested in. It just says the atom carries most of its mass in the nucleus. Cathode rays. Cathode rays were an explanation for the discovery of electrons themselves, not for their nature, just that they exist. Photoelectric effect is also useful for the particle nature of light, right? So we didn't talk about light and the quantized nature of light, but if we had, then photoelectric effect would have been an explanation. Okay, let's see, we got that 12, 13, 14, and 15. Oh, we're going to finish off this page. 16. All right. 16. The 4 lines observed in the visible emission spectrum of hydrogen tell us that, okay, and we mentioned that earlier actually. Let's see if we can pick it out of here. The hydrogen molecules they came from have the formula H4. That's just ridiculous. Right? That's in there. That one's in there just to throw you off. There's no such thing as H4. B, we could observe more lines if we had a stronger prism. No, that's been attempted. Trying to resolve multiple lines that may be buried in a single line. Right? You can't see more lines with a stronger prism. There are 4 electrons in an excited hydrogen atom. No, hydrogen only has 1 electron. That's it. Only certain energies are allowed for the electron in a hydrogen atom. D is the best explanation. The energy level movement of electrons is quantized. And obviously, D and E cannot both be true. D says the energy is quantized. E says it's not. The spectrum is continuous. Well, that's just kind of crazy because continuous means they're not individual lines. It's a continuum, right? It's everything. So D is really the only answer for that one. 17. All right. For which of the following transitions does the light emitted have the longest wavelength? Now, you could actually calculate that value. Right? We would calculate the energy and then convert the energy into wavelength using Planck's equation. But we don't need to. We just need to know a little bit about the structure of the atom and the movement of electrons corresponding with emission of light. Okay, so if we look at the atom, here's the nucleus, and you've got an energy level here. Where's the second energy level? Way out here. Where's the third one? The gap is a little closer. Where's the fourth one? It's even closer. Where's the fifth one? It's closer still. So there's 1, 2, 3, 4, 5. Now, well, we didn't need 5. But notice that, and you have to understand also that the energy emitted depends on the distance of the jump. So from 2 to 1, if the electron jumped from here to here, you'd give off a lot of energy. If you went from 3 to 2, you give off less energy. So the key here is the least amount of energy is given off by the shortest jump. And that corresponds to the longest wavelength. Long wavelength is proportional to small frequency. Which is proportional to small energy. Okay, so a small value of frequency means small energy, which means long wavelength. So with that knowledge, we just need to look for the shortest jump of these A through E. Right? So A, B, C, D, E. A is a jump from 4 to 3. 4 to 2 for the next one. 4 to 1 for the next one. and 3 to 2 for the next one, and 2 to 1. Okay? The highest energy jump is going to be just about anything to level 1. There's a huge jump there. So we can say that this jump from 2 to 1 is not going to fit the bill. This jump from 4 to 1 is definitely not going to fit the bill. So which one of these is the shortest jump? Well, if we go from 3 to 2, that's a pretty good sized jump compared to, well, actually 4 to 2 is a bigger jump than 3 to 2. So 4 won't work. So now it's a choice between 3 to 2 or 4 to 3. 3 to 2 goes here, 4 to 3 goes there. 4 to 3 is a shorter jump. So A would give you the least amount of energy, the smallest frequency, the longest wavelength. All right. So we didn't have to do any calculation. We just had to understand what these energy levels mean and the energy released in any particular jump by comparison with other jumps. Okay, let's see. Let's scoot this back on camera. There we go. Okay, that was 17. Wait a minute, did I? Oh, yeah, we did 16. I just didn't mark it off. 17. Now 18. Oops, there we go.
Okay.
When a hydrogen electron makes a transition from n equals 3 to n equals 1, which of the following statements is true? Okay, so we're jumping from n 3 to n 1. Which position is the lowest energy? N equals 1 is the lowest energy. N equals 3 is the higher energy. So if you go from higher to lower, that means you have to emit energy as you move, right? Conserve energy. If the electron now has less energy, where'd that energy go? The energy went into a light, wavelength of light. So let's see which one of these is true. 1. Energy is emitted. That's true. Energy absorbed, they can't be both true. How about 3? The electron loses energy. In order for the electron to emit energy, it has to lose energy, right? We're conserving energy. So if it loses energy, it's got to go somewhere. Well, it's lost the energy. That's true. 4 can't be right. It can't lose and gain energy at the same time. So 4 is wrong. So let's see what's 5. The electron cannot make this transition. Who says? Electrons make those transitions all the time. In the blink of an eye, they'll make that transition. They go the other way too if there's energy input. So Roman numeral 5 is what I call a filler. It's just completely ludicrous. We need a 5, so we just put that in there. This transition is perfectly legitimate. So B, 1 and 3 are true. Okay, that was 18. Okay, let's skip to 21. Here we go. Now we're looking for the incorrect statement. Let's see, A, B, C, D, and E. All right, so let's see, do we have any composite answers? No, they're all unique. So we just need to find the one that's wrong. Okay, A, the emission spectrum of hydrogen contains a continuum of colors. That's false, because the emission spectrum of hydrogen is a line spectrum. Okay, we found the false one, so the rest of them must be true. B, the diffraction produces both constructive and destructive interference. Yeah, that's true. I described that diffraction characteristic to you, where you have 2 point sources from different slits, and they constructively and destructively interfere. That's a concept that you need to hold on to. Interference, constructive or destructive interference. When we start talking about the nature of the chemical bond, then we're going to, at some point, we look at constructive and destructive interference in the way bonds are formed, right? So hold on to that concept. That's true. B is true. All matter displays both particle and wave-like characteristics. That's also true. Now, large masses moving at low velocity have insignificant wave character. So that's why we think of large objects ourselves as particles, as big particles maybe, and not waves. But we do have wave character. That was the whole idea behind de Broglie's calculations. Okay, so C is true. D, Niels Bohr developed a quantum model for the hydrogen atom. That's absolutely true. He said that the electrons travel in orbits, and they can only exist in those particular orbits. N equals 1, 2, 3, 4. Now, he was right about the quantizing of the electrons in the hydrogen atom, the position of electron in the hydrogen atom, but he was wrong about the orbital theory. They don't travel in orbits. But it was a beginning, and as far as it went, it was true. It was a quantum model. And E, the lowest possible energy state of a molecule or atom is called its ground state. That is absolutely true by definition. So the ground state of hydrogen, right, is where the electron is in N equals 1. It's in the first energy level. That's as close as it can get. There's only one electron. How about helium? Helium has 2 electrons in N equals 1. Both those electrons. Right? And if we write the electronic structure, this will be 1s1 and this will be 1s2. The ground state is as we fill up the orbitals. So if you if you promote an electron beyond its ground state, The name for that is excited state. And anything other than ground state is excited state. All right. So 21 was, answer to 21 was A. Let's see, scoot this back just a little bit. There we go. 21. How about 22? Oops, too far. Which of the following statements best describes the Heisenberg uncertainty principle? Heisenberg. Is it all E's? Yeah, they're all E's. Heisenberg uncertainty principle. What does Heisenberg propose? Heisenberg proposed that whenever you measure the position of a particle, and you also try to measure its momentum, the position, let's see, I'm not sure what the, let me get my terms correct here. Let's see, I'm looking for Heisenberg's formula. I may not be able to find it quickly. If I can't, we'll move on. Maybe I've got it in useful information. Let me see. No, I don't see it. Okay. So we'll let it go and just answer the question. So basically what Heisenberg was saying was, for small particles, if you're looking for the position and the velocity, which means, in his terms, it was momentum, mass times velocity. Well, if the particle's not going to give up any mass, right? So we're really focused on the velocity. You can't know both at the same time for small particles. Now, for large particles like the human body, yeah, you can know them, right? And there's a formula that says if the quotient of these values is greater than, I think it was 4 point something maybe, then you can know both of them. But for particles that are really small, you can't know both, the position and the velocity. So let's see which one of these statements describes that principle. The exact position of an electron is always uncertain. Well, no, that's not what Heisenberg says. Heisenberg says you just can't know both at the same time. The velocity of a particle can only be estimated. Now, sometimes you can say what the velocity is. That sounds kind of weird, you know. If you know how fast a particle is moving, how come you don't know where it is? Right? So Heisenberg was a mathematician, so mathematicians have a way of rationalizing these things, thinking outside the box. Whereas I would say, how can you know how fast something is going if you don't know where it is? Anyway, A and B don't satisfy. C, it's impossible to accurately know both the exact location and the momentum of a particle. That's true. That is the Heisenberg uncertainty principle. D is obviously false. The location and momentum of a macroscopic object are not known with certainty. Well, you can. Heisenberg's formula says that if they're above a certain size, then you can know both at the same time. It's just when they get really small, or the momentum is really high, then you can't know. The location and momentum of a particle can be determined accurately, but not the identity of the particle. That's another filler. Right. C is the only correct answer. That is the Heisenberg uncertainty principle. Okay, that was 22. Now let's skip to, we're doing on time, 25. Now we're going to start talking about electronic structure. Right. So 25 says, how many f orbitals have the value n equals 3? So what are our quantum numbers? Well, we got n, the principal quantum number, which is basically energy level. Then we've got L, which is the angular momentum quantum number. And we got the magnetic quantum number, and then we've got the spin quantum number. Right? So when we're talking about orbitals, we're only interested in these three, right? Because the spin quantum number only references whether the electron in that orbital is clockwise or counterclockwise. So we're really only looking at these three. So how many total can you have in 3 of the f orbital? So now we have to say, if this is 3, what are the possible L's? L's can be either 0, 1, or 2, correct? That's S, P, D. Are there any F's there? No, there are no F's. That's why the answer to 25 is 0, A. Okay, what would it take to give you F's? This would have to be 4 or greater. If you have 4, then you have 1, 2, 3, 4, and you have F orbitals. Okay, but that wasn't the question. The question was n equals 3. All right, that was 25. 27. If n equals 2, how many orbitals are possible? All right. Let's see, 27. 27. N equals 2. That means L equals 0 and 1 as possibilities. And we're totaling up the maximum number of orbitals at that level. How many orbitals are possible, right? So remember, these are cumulative, right? They expand. So M sub L would be what? Well, this one can only be 1. That one. This one can be -1, 0, +1. That's all the orbitals. 1, 2, 3, 4. You can have 4 orbitals if n equals 2. Right? So that's why the answer is B, 4 orbitals. If you need more, you got to go to a higher energy level. All right. Let's see. We're going to do 28 and 29. Okay. So 28. A given set of p orbitals consists of how many orbitals? So here we're saying, doesn't matter what n is. We're looking at L, and P corresponds to what number? Right? S, P. This is 0, this is 1. So what they're actually asking is how many M sub L's can be in P? -1, 0, +1. You can only have 3. Right there, 3. All right, That was 28. And 29 coming up. Which of the following is an incorrect designation for an atomic orbital? Okay, this is going to take a little bit more work. Which one's wrong? B, C, D, E. All right, we've got 1s. We've got 3D, 1p, 4f, 6s. All right, let's take them by letters. Right? Can you have a 1s orbital? Yes, in fact, hydrogen and helium both have 1s, and anything above them can have 1s as you build toward the maximum in that element. So that one's true, and that one's true. So what's next? P. There's a P. Can you have a p orbital at n equals 1? Well, no, n equals 1, then L equals 0. That's it. Nothing more. You can only have one. You can only have as many L's as there are N. So you can only have a 1. So this one is false. We found our false one, right? 29. Which one's incorrect? It's that one. How about these others? If n equals 3, right? You can have 0, 1, 2. S, P, SP, D. That's true. If n equals 4, you can have 0, 1, 2, 3. S, P, D, F. That was true. So 1p is the only one that is false out of that group. All right, let's see. I got a half hour left. How am I doing on time? I'm running out of time, so I need to move it. All right. There we go. So I'm going to have to start being selective. 31, we do need to do that one. This is definitional. A point in the wave function where the amplitude is 0. Remember the wave function diagram where we had that? And we had, let's see, energy and distance. Right? For the s orbital, you have 0. This is at the nucleus, right? So the 1s would do this. The 2s would do this. Let's see. Like that. So that would give you a 0 probability of finding electrons at that distance. That is a node where the amplitude of the wave function is 0. And the amplitude refers to how high it is, right? This has some positive value in energy, but at this point, the energy is 0. And you know what? This is not right. It's not energy. It's psi squared. The probability of finding electrons. That's what that is. My mistake. So the answer to this one is a point in a wave function where amplitude is 0 is a node by definition. You don't need to go any further. That was 31. I took a long time to explain that one. Okay, let's see if any of these others, if we need to stop it at any of these others. 32, how many electrons in an atom can have the quantum number 3 and L equals 2? How many electrons? All right, we'll do one of these. 32. All right, if the quantum numbers are N equals 3 and L equals 2, how many electrons maximum can you fit in the orbitals below that, right? Well, is that true, right? You could have 0, 1, or 2, all right? So that's true. But now we're only focused on this one. So M sub L would be what? Minus 2, minus 1, 0, plus 1, plus 2. And each one of these has 2. So how many is that? 1, 2, 3, 4, 5 times 2 for the spin number, right? That's what this is, equals 10 electrons. You can have 10 electrons with these two quantum numbers. Okay? We're going to skip 33. Let's see, 32, 33. Yeah, we're going to have to move along to be sure and get to some of the topics that we haven't covered yet. Okay, we'll look at 37. Which one of these combinations of numbers are not allowed? And that is 37. Yeah, 37. Okay, the first one is 9, 8 minus 4, 1/2. 9, 8 minus 4 plus 1/2. Second one is 8, 2, 2 and 1/2. And 6 minus 5 minus 1 and 1/2. And 6, 5 minus 5, 1/2. 6, 5 minus 5, 1/2. Okay. I think it's safe to say that 1/2 is allowed for any of them. It just says that electron has a plus 1/2 spin. And all of them have that. So we're not going to disqualify it based on this one. So we got to look at these three: the N, the L, and the M sub L. Okay. All right. So, is this allowed? Well, if this is N, you could have L's could be 0, 1, 2, 3, 4, 5, 6, 7, 8. 9 of them. So 8 is allowed. Is minus 4 allowed for 8? Well, yeah. It's minus 8, minus 7, minus 6, minus 5, minus 4. That's allowed. So that one's okay. How about this one? 8. So you could get 0, 1, 2. There it is. Right? So that's allowed out of this one. How about 2 out of that one? Well, 2 would be minus 2, minus 1, 0, plus 1, plus 2. That one's allowed. Right? So all of those are allowed. We're good there. How about this one? If N equals 6, you could have 0, 1, 2, 3, 4, 5. That's a negative 5. In fact, you cannot have a negative number for L. It starts at 0 and it ends when you've got the same number as the n value. 0, 1, 2, 3, 4, 5 plus positive 5. So we found our wrong one. And E says all are allowed, which means E's wrong also because we can't allow C. So D is also valid. All right, that was 37. All right. 37, let's see. Let's see, 40. We can knock that one out pretty quick. Who is the first chemist to recognize patterns in chemical properties of elements? The temptation is to say Mendeleev. Mendeleev was not the first to recognize patterns, right? It was Dobereiner. Dobereiner came up with relationships, called them triads, of elements that had similar properties. Okay, that was 40. Let's see, is it worth stopping at 41? Yeah, we can knock 41 out. 41 says, Mendeleev is given most credit for the concept of the periodic table of elements because, why? Well, he recognized patterns, right? But the real, the golden nugget in Mendeleev's periodic table was prediction. He left empty spots in there where he predicted there would be elements. Not only that, he said they would have these characteristics based on their group and based upon their position in periods. He said they would have these characteristics. Sure enough, they found them. So that would be B. He emphasized its usefulness in predicting the existence and properties of unknown elements. That was Mendeleev's real claim to fame. All right, 44. The complete electronic configuration of 10, you might as well do this one. 44. All right, where's 10? What's the symbol for 10? SN, Latin stannum. So you look at your periodic table, you find SN, right, it's right down here, as 50 electrons. Okay, this is going to take some board space for 50 electrons. So I'm going to start way over here and be sure I've got room. Yeah, there we go. So we do, you know what? Let's use the periodic table. Right? Remember, the periodic table is subdivided. These two groups are filling s orbitals, and the s orbitals correspond to the period numbers, right? 2s, 3s, 4s, 5s, on down. These are p orbitals, and they also correspond to the period numbers. So these would be 3s, these would be 3p, 4p, 5p. So we're going to have 5 p's for 10. There's 10 right there. How about these? Well, these jump down from 4 to 3 on this period. And these are d orbitals. These are all d's. So we can use that. We don't encounter any f's because they're down to period 6. All right, so we don't have to worry about f's. We're only going to have s, p's, and d's. All right, so let's use our periodic table. And we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we're getting into transition metals. 3d. How many can we have in d? Let's see. S is 0, p is 1, d is 2. -2, 1, -1, 0, +1, +2. 5 suborbitals with 2 each. So that's 10 electrons. Okay. Then we go back to 4p. Fill it up. Now, at this point, we're out here at Krypton. Right? Now we're going to get into the period that has 10. So we have 5s, 2, and then we have 4d, 10. Right? 4 Ds right here, right here, starting with the yttrium, go across here, and then we go back to 5 Ps, and we're 2 indium 10. We're 2 5 Ps. That's the complete electronic structure of 10. And let's see which one fits that. Let's see, 4 has 3. D. D fits that complete electronic structure. Now, how would we abbreviate that? Well, you work your way back until you find a noble gas. So we got 10, and we work our way back. Krypton. Krypton 36. So Krypton 36 takes care of 4s and 3s up to here. And then the rest of them are 10. That's the abbreviated version. Oh, well, it didn't ask for that, but that is the abbreviated version of 10. Now, which are the valence electrons? Right? The valence electrons are the electrons with the highest N number, the highest principal quantum number. So there are 2 here and 2 there in the 5 level. Don't count the 4s because that's 1 step less. Right? So we have 2 and 2 is 4. 4 valence electrons for 10. All right. Okay. And I got 15 minutes left. I'm probably going to run out of time. So I'm trying to abbreviate this, but I'm definitely going to finish it, whatever it takes. Definitions. 46. The statement that the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals. In chemistry, degenerate means same energy level. So a p orbital, like 3p, would have x, y, and z. Right. These suborbitals are degenerate. That is, they're the same energy level. And you would fill them up like this, 1, 2, 3, and then you go back, fill them up like that. Right. That's Hund's rule. That's Pauli exclusion principle. But based on the Pauli exclusion principle, the lowest energy configuration of an atom, now that is Hund's rule. Unpaired electrons allowed by the Pauli principle. So Hund's rule says you have to fill up the spin ups first, and then you can go back and start filling spin downs. The Pauli principle simply says, the Pauli exclusion principle means that no 2 electrons can have the same set of quantum numbers, the same set of 4 quantum numbers. They are unique sets. So the answer to 46 is B. All right. Let's see. Okay, we'll do 47. So if you're given this abbreviated configuration, can you tell whether the element is a non-metal, a transition element, metal, lanthanide, or actinide. By process of elimination, it can't be an actinide or a lanthanide because there are no f orbitals in there, right? Actinides and lanthanides are filling f orbitals, so that's out. So now we need to say, is it a metal or a non-metal, right? So you look at the highest energy level, 5p2. So you go over 5p2, and you can actually find the element. So here's 5, and here's the p's, 1, 2, that's 10, right? We did 10 before. That's a metal, right? Because it's to the left of that zigzag. All right. 48, an element with a configuration 4f14. But what does that mean? 4f14 means it's full. Because F can have 7 suborbitals, and each one can have 2 electrons, so they're 14. F is full for this one. So 5d is what you concentrate on. 5d7. Let's see, 5d. How would you get to 5d? You actually start with 6. And then when you get to lanthanum and over, these are 5ds. 6s, 5d, 6p. Right? So the 5d is a transition metal. Notice also that the d is not full. D can have 10 electrons. It's only got 7. So we're still in the D-filling region, which is transition metals, transition elements. That's why A is the answer. All right. Let's see. How many valence electrons is an alkaline earth? Which group is it in? It's in the second group. So it only has 2 valence electrons. That's why when it loses those 2, it has a positive, a 2+ charge. Right? We just memorized the groups. The first group is 1+ charge, second group is 2+ charge. This is why, because it loses both of those valence electrons. And now the imbalance is toward 2 extra protons because you lost 2 electrons. That gives it a 2+ charge. Okay. Let's see. Let's look at we're gonna let's look at 52. I'll just go past the time as usual. 52. Okay, so 52 is iron. Excuse me. Yeah, iron has how many unpaired electrons in the d orbital? All right, so iron is 26. Right? It has a 1s2, 2s2. Let's write the abbreviated one. Argon is 18. So what's left over after argon? We get to 4s2. And then we get into the Ds. 3d. And how many electrons are there? Well, let's see. 1, 2, 3, 4, 5, 6. 6 electrons. Okay? So how many unpaired electrons are there? Well, how many orbitals are there in D? There are 5, aren't there? 1, 2, 3, 4, 5. So we start filling them up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 4 unpaired electrons. That's why the answer is D. Let's see, how about 53 and 54? Nitrogen has 5 valence electrons, that's true. There's 2 s electrons and 3 p electrons. So how do those p electrons go in there? Which represents the ground state? Well, the 2s orbital has to be full before you can get to the p. If it's in its ground state, then everything is as low energy as possible. Right? So if it's got 5 valence electrons, then you can't have 1, 2, 3, 4, 5 in this configuration because you've promoted one of these s electrons. One of these s electrons. So it can't be B or C. It has to be A, D, or E. Then you go look, how do you fill them up? Right? You fill them up, well, actually D can't be right because there are only 4 valence electrons. But you don't fill them up, well, E can't be right either because that's 2, 4, 6, that's 6 valence electrons. Okay, so after that argument, the only one that can be right is A. 1, 2, 3, 4, 5. These have to be up before you can have any downs, and there are no electrons left. So A has to be it. What if you add an electron? Notice this one, N minus. Where does that electron go? That electron adds another electron. So now it has 6 electrons. So where does it go? Well, it has to go paired up, right? So here we have 2, here we have 2, here we have 3, here we have 4, and that 4th one goes right there. Okay? That's the N minus ion. All right. Let's see, I got 5 minutes and got several pages left. So let's see. I'm going to skip down. '67. There it is. Which of the following processes represents ionization energy? How do we tell ionization energy? What is required to measure ionization energy? First, you need the element in the gaseous state. So in this case, we have bromine, right? Normally, bromine at standard temperature and pressure is going to be Br2, right? Br2, and it's going to be a liquid. But we can't use that for ionization energy because some of the energy we put in there is going to have to break the bromines apart first, change them to gas first, individual atoms. Then the extra energy goes into ionizing an electron, right? So we can't use that. We have to use this one, right? Then we add some energy to it, and it promotes an electron to infinity. And it takes energy to do that. Right? So the one that satisfies that condition is C. All right. Let's see. I think ordering in increasing ionization energy 68 and 69, increasing atomic radius, you can do that simply because the trend will tell you what to do. Lower left to upper right, what happens? Ionization energy increases. So you just take sulfur, chlorine, and fluorine and say, what are they in relation to one another? and you can order them correctly. 69 is atomic radius, right? What do they do when you go from a lower left up right? They get smaller, don't they? Right? So instead of bigger, it gets smaller. Let's see. How about 73? 73. Of the following elements, which has the lowest first ionization energy? Well, no, that's not. You can figure that one out. I'm looking for okay, 80s, those are repetitious. 85. So let's scroll down to 85 here. Which of the following equations correctly represents the process involved in electron affinity? Okay, electron affinity is not the converse of ionization energy. Electron affinity starts from the same place as ionization energy. It starts from the gas of the neutral atom, and then it adds an electron. Now, when that happens, you get energy back. In other words, energy leaves, right? Which means the energy is negative. The sign is negative because energy has to leave the system. The system is right here. And as an electron drops from infinity to the lowest possible, the lowest available orbital, it gives up energy. All right. So the one that satisfies that condition is C. Right there. Okay. Let's see. Right, I might come back to 87. Actually, I'm already over, so I'm going to take a bathroom break and I'll be right back. If you need to go someplace, that's fine. I'll just keep recording. But I'll be back in 3 minutes. Let's see, where was I? Oh, 87. 87. I'll come back to that one. Let's see. I lost my picture. Hold on a second. There we go. There we go. Let's see, is 88 worth looking at? No, we've done one like that before. Okay, let's go down to 90. There we go, 90. Here it is, 90. All right. What is the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from n equals 5 to n equals 1? All right. We've been, you know, that is missing a piece of information. I just noticed that. I've got it on the key here, but it's not there. The wavelength of light is emitted because we're dropping from energy level 5 down to energy level 1. So we're going from a high level to a low energy level, which means we're giving up energy. All right. The problem is you're not given the energy for n equals 5. You need that. So let me add that. Let's see, can I do that here? Edit. Yeah, I can add text. So let's say here, n equals 5. And then that corresponds to a negative 0.08712 times 10 to the minus 18 joules. Okay, now I need to take that 18 and make a superscript out of it. There we go. Now, it's a little offset, but the information is there. I better save that. There we go. Okay, now we can answer the question. So if we're going from n equals 5 to n equals 1, it's the same calculation as if you're saying, what's the temperature change in thermochemistry? N equals, if the temperature goes from 90 down to 10, then 10 is the final, minus 90 is the initial. So it's a minus 80 degrees that you moved. So we do the same thing here. We say, what's the final? N equals 1. So n equals 1, the change in energy equals n equals 1 final minus initial. So let's see, final is minus 2.178, minus 2.178 times 10 to the minus 18 joules, minus a minus 0.08712, 0.08712 times 10 to the minus 18 joules. So that's the energy. Now, why are we bothering with the energy if the question asks us for the wavelength? Well, we can't go straight to the wavelength from energy. We need to calculate what is the energy of that photon. Then we can convert energy of the photon to wavelength using Planck's equation. Okay, so what is the difference here? Well, let me see. See, notice these are 10 to the minus 18th on both sides. So 10 to the minus 18th is going to be the exponent. And all we have to do is this part of the calculation. So let's see, 2.178, change the sign. Okay, then plus, minus, 0.0871. So minus 2091. Minus 2.091 joules. All right, here's the trick. This energy is being emitted. So once you know that it's being converted into light, then you don't need the minus sign anymore. You only need the minus sign if you're trying to decide, is the energy being emitted as light or being absorbed? If it were being absorbed, that value would be positive. But for the calculation of the wavelength, we don't need the negative sign. We just need the absolute. So, excuse me. Change in energy is equal to Planck's constant times frequency, and frequency is c divided by wavelength. Remember that? Okay, so this energy here, the absolute value of that energy is equal to Planck's constant, 6.626 times 10 to the minus 34 times the speed of light and wavelength. So we'll solve for the wavelength. So the wavelength's going to come over here, and then we're going to have this one go over there, swap places. So this is going to be 6.626 times 10 to the minus 34. And then speed of light, 2.9979 times 10 to the 8 meters per second, divided by 2.091 times 10 to the minus 18. And that should be the wavelength in meters. And speed of light, and then divide by 9.50 times 10 to the minus 8. 9.50 times 10 to the minus 8 meters. Let's see. There it is right there. B. There. Okay. All right, that was 90. Might as well while we're here, 91. Let's see, let me, there we go. Let's get this out of the way. That's good. All right. What did I say? 91? 91. Which of the following is a reasonable criticism of the Bohr model of the atom? It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Actually, it does. Bohr said the electrons don't fall into the nucleus because of their momentum. They're moving fast enough. It's like a satellite circling the Earth. If it moves fast enough, it stays out there. So that's what Bohr claimed. The electron was moving fast enough so it stayed in its orbit. It does not adequately predict the line spectrum of hydrogen. No, it accurately predicts the line spectrum and the wavelengths of each of those lines. How about C? It does not adequately predict the ionization energy of the valence electron for elements other than hydrogen. That's true. If you get more than one electron and more than one proton in there, the model tends to start to fall apart. So that's a valid criticism. Okay, that was 91. C's the answer. All right. Let me see how many more I got to go. A few. Okay, we can spend time on this one. 93. Which of the following statements is or are true? So there could be more than one. How about Roman numeral 1? 93. An excited atom can return to its ground state by absorbing electromagnetic radiation. No, the ground state is low energy. So absorbing more energy would just make it higher. It can't return to the ground state by absorbing energy. It has to give up energy. So 1 is false. How about 2? The energy of an atom is increased when electromagnetic radiation is emitted from it. The energy of an atom is increased. No, it's decreased. When it loses energy from the system, the energy of the atom decreases. So 2 is false. How about 3? The energy of electromagnetic radiation increases as its frequency increases. Yes. Energy directly proportional. Right? As this one goes up, that one has to go up. Frequency increases with energy. So 3 is true. How about 4? An electron in the n equals 4 state in the hydrogen atom can go to the n equals 2 state by emitting electromagnetic radiation at the appropriate frequency. That is absolutely true. A jump from n equals 4 to n equals 2 will emit radiation of a specific wavelength. And 5. The frequency and wavelength of electromagnetic radiation are inversely proportional to each other. If the product of two variables equals a constant, then the variables are inversely proportional to each other. In order for this to remain constant, if this one goes up, the other one has to go down, vice versa. 5 is true. Okay, so 3, 4, and 5 are true. That's D is the answer. All right. That was 93. Let's see what else I've got. I'm just going to give you 94. Let's say an electron is found in a 2p orbital. Which one of these statements describes the movement of electrons in a p orbital? Actually, the movement of electrons in an orbital, in any orbital, cannot be exactly determined. That's why quantum mechanics is based on statistics. It's probability. Where are you most likely to find electrons? Right? So it's mapped out in density. Electron density will be very high in this region. But that doesn't mean you can find the electron anywhere in there, in any one position. It's just most likely to find it there. It's like I had a professor tell me one time, describing probability. He said, there's a very, very, very tiny, small probability that all the air molecules in this room will migrate to that corner and we'll suffocate. Okay, that's probability. You know it's not going to happen, but statistically speaking, there is a finite probability that that will happen. We don't stop and think about it a lot because the probability is so small. All right, 95, we've done that one before. How about 97? What does it look like? Okay, 97. Which of the following is not a property usually predicted by Mendeleev for an undiscovered element? What did Mendeleev know at that time? They knew a lot about oxides of elements. They knew that. They could predict that. Boiling point, yeah, he predicted that. Physical properties, density, predicted that. Atomic mass, he predicted that. What he could not predict was electron configuration, because the work had not been done yet. Right? The theories behind where electrons are most likely to be found in orbitals around an atom hadn't been done yet when Mendeleev was there. So naturally, he didn't make any predictions about that. So A is the one that Mendeleev has nothing to say about. Okay, which of the following atoms or ions has 3 unpaired electrons? You just need to draw the electronic configuration. And remember, if you have degenerate orbits, right, at equal energy levels, like P's have 3, or D's have 1, 2, 3, 4, 5, or F's have 1, 2, 3, 4, 5, 6, 7. Then you start with the electrons that go into those orbitals, and these will be the highest level orbitals, of course. Then you say, all right, you go in like that, like that, like that, and then you start pairing them up. Right? You have to go in unpaired first, then pair them up. And just do that for each one of those. And you'll find out which one has 3 unpaired electrons. As it turns out, nitrogen is the only one. And don't forget, if you have an ion, this 2- means you add 2 more electrons than the ground state. Okay. If it's a positive charge, that means it's lost electrons from the ground state. So titanium will be 2 less electrons than its atomic number. Keep that in mind. All right. 101. This is an interesting problem. There we go. All right. 101. An element E has the electron configuration, Krypton as its core, then 5s2, 4d10, and 5p2. That looks like 10 to me. We did that one before, didn't we? The formula for the fluoride of E is most likely what? Well, how many valence electrons are there? There are 4 valence electrons. So the most likely ionization of this element will be to lose 4 electrons, right? Because fluoride isn't negative. Fluoride is very strongly electronegative, so it's going to extract electrons, right? And make E positive. So E can lose 4 valence electrons, and then you combine it with fluorine, which has 1, you need 4 of those. So EF4 is the most likely compound of fluorine with E. Now there are other possibilities, but that's the most likely one. All right. let's see, 104. Let's see what 104 has to offer. All right, this is a good one. Now we're talking about second ionization energy, 104. What are our choices? All right, A, B, C, D, E. We have magnesium, chlorine, sulfur, and calcium and sodium. Okay. So, first ionization energy, let's say, where are these located? Sodium, let's see, sodium, magnesium, and calcium's down here. Sulfur's over here. And where did I leave that? Chlorine. Chlorine's over here. All right. Look at the valence electrons for each one. In order to have the largest second ionization energy, I would suspect that you would want to find the one for the second ionization energy that gets into the core electrons. So sulfur and chlorine, chlorine has 7 valence electrons, sulfur has 6. They got a lot of electrons to lose before you get to the core. So sulfur and chlorine, we can let those out. How about magnesium? Magnesium and calcium both are alkaline earths. They have 2 valence electrons. So the first and second one, the second one's going to be more energy than the first, but it's not going to be the largest for the whole group. Now the ionization energy for magnesium is going to be higher than calcium, but their second ionization energies are not going to be the greatest. Sodium, however, is an alkali metal. Its first ionization energy is going to be a value, but the second ionization energy tries to remove a core electron. That one is going to be huge by comparison. Okay, that's the key to this question. Which one gets into the core for the second ionization? All right, so that's 104. Let's see, now I'm going to skip over to, let's see, does this one have anything to shed light? Which of the following, 107, which of the following concerning second ionization energies is true? Okay. If you read all of those down there, really the only one that fits is, well, first of all, C and D can't be true. The aluminum is lower in second ionization energy than magnesium. They're both valence electrons, but aluminum is not lower. Aluminum second ionization is the same as the first in these terms because you're still valence electrons. And the value for aluminum second ionization energy is actually higher than magnesium because the trend is lower left to upper right, and aluminum is to the right of magnesium. All right, so you can throw out C and D. You can throw out E too because the second ionization energies are not going to be equal. Why? Because aluminum has an extra proton pulling on those electrons. Right? So they can't be equal. Aluminum can't be lower, so it's either A or B. So if aluminum is higher in second ionization energy than that of magnesium, why? because magnesium wants to lose the second electron? No, there's no wanting about it. Because magnesium, because the electrons are taken from the same energy level, which is true, right? They're both principal quantum number 3, same energy level, but aluminum has an extra proton. So B satisfies. It has one more proton than magnesium, which means there's an unshielded positive charge addition pulling on that electron. So B is the answer to 107. Make a long story short. Let's see. Consider a planet where the temperature is so high that the ground state of an electron in hydrogen is N equals 4. What's the ratio of ionization energy for hydrogen on these planets? Okay, we might come back to that one. Let's get the rest of them done first, and then I've got 2 saved already. Oh, that's it. That's the only ones I have marked. So while we're here, we'll look at 10. Nope, that's not it. 108. 108. Yeah, 108. Okay. So, what's the question? What's the ratio of ionization energy for hydrogen on this planet compared to that of Earth? The ratio of ionization energy. Let me see what's going on over here. What are you doing? Stop that. The ratio of ionization energy. So the ratio of ionization energy of hydrogen on the planet compared to the Earth. Okay. So we need to get them in order. Ionization energy of the exoplanet, ionization energy of Earth. That's the ratio we're looking for. So we need to know what those ionization energies are. All right. So if the exoplanet has a ground state electron at N equals 4 versus N equals 1, N equals 1, N equals 4, how much energy is it going to take? Let's do it qualitatively first. How much energy is it going to take to remove an electron from a hydrogen atom on Earth? A lot. Is it going to take more or less for the exoplanet? It's going to take less because it's already at energy level 4. The transition to infinity is less for this one than that one. So that means the ratio is going to be less than 1, right? This value is going to be a lot less than that one. We just need to know what it is. Okay, so how do you determine the ionization energy, the energy of transition? Well, it's final minus initial. So the transition energy here is equal to energy at infinity minus the energy at 4. Right? Initial, final minus initial. Whereas the one for Earth is equal to infinity minus E1. Okay. Now, how do we calculate these energies? Well, what's the energy at infinity? It's 0. Is it not? Yeah, because everything, as you get closer to the atom, becomes more and more and more negative. You're starting at 0 infinity, 0 energy relative to the nucleus, right? So if we ratioed these two terms, like this, then that ratio would simply be e to the 4th divided by e to the 1st, right? And the negatives cancel. So what's the energy at level 4? Well, let's see. We're not given that, are we? All right. The formula then for energy for any of these energies is minus, is this constant, minus 2.178 times 10 to the minus 8. Minus 2.178 times 10 to the minus 8. Times 1 for hydrogen, divided by the N number squared. Okay? So what it is for 4, right? It'll be that constant. Let's just say it's minus K. This is K. Minus K times 1 over 4 squared. And this is minus K. Well, let's keep the negative signs here. Negative, negative. That means this is positive, positive. Because it's going to be a minus K, minus K. And no, let's leave it that way. Minus, minus. There we go. And then this one, the ground state on Earth is 1 over 1 squared. Okay? So, this is going to be, these cancel, right? This is going to be 1 over 16. This is going to be 1 over 1. So what does that mean? This is 1 divided into 1/16, which is 1/16. So the ratio here, this ratio is equal to 1 divided by 16. That's your answer. 1 divided by 16, not 16 divided by 1. Or 1 to 16 is the ratio right there. Okay. All right, now we have one other one that I want to do, I think. Let me look, see. That we skipped earlier. Let's go back. Be sure I didn't circle any others. 87. Yeah, 87. All right. Let's see. Let me do this quickly. 87. There we go. Oops, excuse me. Okay. What are we given? Well, what's the question? We're going to find out what element this is based upon the information given. So, what element is it? And what are we given? The atom is traveling 1% of the speed of light. So its velocity equals 0.01 times 2.9979 times 10 to the 8 meters per second. That's its velocity. 1%, 0.01 is the decimal equivalent of 1%. That's its speed. The de Broglie wavelength is found to be 1.46 times 10 to the minus 3 picometers. Okay? Now, what do we need to know to determine the identity of the element? Well, like I've always said, if you know the atomic number, you can find it. Maybe you don't have that. But the question is, can we determine the molar mass of the element? Right? Do we have enough information to determine the molar mass? Well, what would be the mass of the element? Right? Don't we have an equivalence for mass and energy? Right? Don't we have, what's the equivalence of mass and energy? E equals mc squared. Right? That's if it's at the speed of light, but it's not at the speed of light. So the energy for this element, this atom, is actually you know what we need is the de Broglie equation. Yeah, that's what we need. The de Broglie equation says that the wavelength is proportional to Planck's constant divided by the momentum, mass times velocity. Right. It's just that simple. Let me see. Do I have that in the useful information? That's a good question. Let's see. De Broglie wavelength. Ooh, don't tell me I left it out. Oh, there it is. Yep, it's in there. That's the de Broglie wavelength. So now we have a relationship for the mass. Okay. We have the wavelength. We have Planck's constant. We have the velocity. So we can find out what the mass is for that one atom. Right? If you know the mass of the atom, you can determine the molar mass. All right. You just need a mole of them. Once you find the mass of one atom, you can find the molar mass by converting it to moles. All right. So here we have, we need to rearrange this for mass, don't we? Put mass over here and wavelength over there. So let's see. Mass equals Planck's constant over wavelength times velocity. There we go. So let's see. Planck's constant is 6.626 times 10 to the minus 34. Joule seconds, excuse me. And wavelength needs to be in meters. So how many meters is a picometer? Well, a pico is 10 to the minus 12th of a meter. So if we take that, 1.46 times 10 to the minus 3 times 10 to the minus 12 meters. So it'd be 10 to the minus 15. So it'd be 1.46 times 10 to the minus 15 meters. And the velocity is 0.01 times that. So this is 10 to the minus 2. That makes this 10 to the 6th. There we go. Now, not to confuse, this is meters, not mass. Okay. Okay, so what's the mass of an atom? The mass of an atom is, crunch the numbers. 6.626 exponent 34 change sign. Divided by 1.46 exponent 15 change sign. And then divided by 2.9979 exponent to the 6th power. So I get 1.5138. 1.5138. 1.5138 times 10 to the minus 25. What's the unit of mass for this one? All these are standard values, SI units. So this would have to be in kilograms. Right? How do I know that? Because joule is a unit of energy, right? And the unit of energy, joules, is equal to 1/2 mv squared. Mass is kilograms, meter squared per second squared. Kilogram meter squared per second squared is a joule. So I know that's kilograms per atom. All right, now we can take that and convert it to grams per mole. So I'm going to have to erase some of this stuff. And make a little bit more room here. All right. So we're starting with, I'm going to start over here. 1.5138 times 10 to the minus 25th kilograms per atom. The rest of this problem is dimensional analysis. We need to get to grams per mole. So you do one unit at a time when you have multiple units that need to be converted. Kilograms, cancel kilograms, give us grams, 1,000 grams per kilogram. Okay, now we can convert atoms. So how many atoms in a mole? Right, we want to cancel atoms. 6.022 times 10 to the 23rd. There we go. Number crunching time again. So I still got this number in my calculator. Multiply by 1,000. Divide and multiply by 6.022, 10 to the 23rd. So I get 91.2. 91.2 grams per mole. Right. So we just look it up. You can usually identify an element from its molar mass. 91.2. So let's get 91 here. Is this 91? Follow along till we find 91. Looks like zirconium. Zirconium. That's the element. I know that's a lot of work, right? But it can be done. You just have to be methodical about it. All right, I think that's probably enough for one day. And the test on this one, this chapter will be due next Monday. And Monday we'll jump into chapter 8 on the nature of the chemical bond. Chapters 8 and 9 both. But we're going to have separate exams. Chapter 8 will be an exam. Chapter 9 will be an exam. And then we'll actually have time to review for the final.